Going, everybody? I'm Arham, a PhD student in Ian and Kyle's lab. I'm going to be talking about some of the systems level work we've been doing on the Aurora GPT project to enable training large foundation models for scientific workflows. And in particular, on the data processing end of that effort, trying to actually deduplicate increasingly large data sets of text data for the purposes of LLM training. And the real need for this kind of scalable deduplication and text processing algorithm becomes apparent when you start to consider the size of modern text data sets. I mean, even the most mundane ones like C4 or StarCoder now are, several hundred gigabytes or a few terabytes in the case of something like Bloom or Red Pajama. And when you look at the most ambitious providers, this is true even to the extreme, where you can start to get text data sets that are tens of gigabytes in size, and that's only growing. In fact, we actually know that it's growing because we have evidence that language data sets roughly double in size every year. And so the need for scalable data processing, scalable text processing, and specifically scalable deduplication is increasing year on year. And simultaneously, we have to be aware that as the scale of these data sets is increasing in terms of number of tokens, we still need to maintain the actual quality of the data sets. And this is one of the reasons why deduplication is actually highly important. Um, if you can't deduplicate between your training data set and your evaluation data set, this skews all of your evaluation metrics. It can also harm the actual nature of your model post-training. It can lead to artifacts like memorized sequences. This has negative impacts on user trust and safety, privacy. This can open you up to legal problems, and it's generally an undesirable behavior that's indicative of something that in classical machine learning we would call overfitting. And so, these are really great reasons to care about deduplication, but another great reason to care about deduplication, particularly at scale, is because it actually allows us to make the model better if we can deduplicate the training data set. And that's because we can actually exercise precise control over the training distribution of the model. This is a seriously underrated part of the training recipe for GPT series models. They've been doing this since GPT-2 and GPT-3, selectively upsampling super high quality subsets of their training data to make sure that their pre-trained language model, their base model, performs as well as possible. And so these are all great reasons to actually care about deduplication. Not only do you care about the scalability with which you can process your text data, actually get it into your model, um, you actually care about the quality of your model, and you also care about the validity of your experimental results. So how do people actually tend to do this in practice? There are some really simple approaches, some more complex approaches. One approach from Meta is that of CCNet, where you essentially normalize a bunch of text data, say to lowercase and then Unicode encoding, and then you literally just compute a SHA-1 hash of that data and compare those hashes directly. This sounds a little stupid, but this is not so unreasonable if you're dealing with large data sets that come primarily from web scrapes, because many internet web pages and documents are going to be exact duplicates of one another and are simply the same document or the same website hosted on mirrors, for instance. Another common approach is to filter based on metadata. So you can imagine you have authors lists or abstracts for scientific documents, or you have something like URLs for web pages or other forms of documents. However, metadata is not always available, and so this isn't the most reliable approach. Similarly, something that OpenAI has professed to do is to filter some data for quality using classifiers and then apply an algorithm called MinHashLSH. We'll explain what that algorithm does in just a moment. And some other things that you can do is, for instance, try to insert documents into a Bloom filter, and then see whether or not they overlap with other documents in the data set. And you can do that by simply directly inserting n-grams or even entire paragraphs from those documents into the Bloom filter and just seeing how many collisions you get. And if you receive collisions over a certain threshold, then you just mark that document as a duplicate. So these are all reasonable ways to deduplicate documents, but they don't generally scale. And we're gonna look at one of the most popular ones in just a second. So MinHashLSH is one of the most widely used algorithms to deal with this problem in practice, particularly for LLM training. This is because, as opposed to a method like CCNet, which compares hashes of documents directly, MinHashLSH can actually fulfill another function, which is to find fuzzy, quote unquote, duplicates of documents. This is really important because you can imagine that when you're scraping lots of documents from the internet, there are many documents that, for all intents and purposes, are duplicates, but only differ by minor variations in the text, in the metadata, and that can completely throw off algorithms that try to find complete or exact matches between documents. This is one of the reasons why MinHash LSH is so popular. One example of this is something like if you have an academic publication and then you extended it to a journal version, or say that you had a preprint of a paper and then you had a conference publication version of that paper, they're largely the same. The semantic content is the same, and we don't want to show it to the model twice necessarily. But exact match algorithms are simply going to fail to find that kind of duplication. So exact match based duplication algorithms such as CCNet are simply widely under-inclusive of the kinds of duplication that we care about. And so particularly for text data, it's important that we use fuzzy deduplication algorithms that are capable of giving us a sort of continuous sense of the degree to which two documents are duplicated. And so the inside of MinHash LSH is to treat documents as sets of n-grams. And in doing so, you can apply a very common metric called the Jacquard similarity to measure how similar two documents are. Then you can simply set your threshold and determine a hard cutoff, say at zero point 0.8 Jacquard similarity. I'll mark two documents as a duplicate. Now, actually estimating the Jacquard similarity for two documents is going to be very computationally expensive. So we actually have a couple of tricks to make this way more efficient. And this is the core of what MinHash LSH actually does, is makes Jacquard similarity between sets really efficient to compute. And so if you just think about the matrix representation of a set of sets, if you look at this diagram on the left, I promise this might look a little noisy, but it's not actually that complicated. On at the column level, you have a number of sets, right? So we have four sets here. And at the row level, we have possible elements of those sets, right? So the universe that we're dealing with has maybe 5 objects, and we have 4 sets that we're looking at. For each set can actually be represented as a binary vector, right? Which just tells you, like, do I have the element at index I inside of this set? And so you can actually just get a very rich representation of your set from this representation. It turns out that if you take random permutations of this matrix and then you measure whether or not the first item that you encounter between these two sets that has a 1 in that row is the same, that is actually probabilistically an estimation of the Jacquard similarity. And this kind of makes sense. If you think about it, like let's say that I take these columns and I randomly permute them, the probability that I will get two items that have the value 1 that are the same item is precisely the actual intersection, right? It's precisely the cardinality of the intersection of those two sets. And in the denominator, you'll end up having the actual union of those two sets, which is, either any pairs that they both have or any pairs that only one of those two sets has. And so it's a little bit complex. You have to have some idea of set theory to actually look at this. But generally, like what you should take away from this slide is that over time, if you sample more permutations from this matrix, you will get a better and better estimation of what the actual Jacquard similarity for that set is, or for those two sets are. However, this is still not efficient enough because if you imagine if you have 10 terabytes of data, you still have to actually compare all of those documents pair by pair. And so we want to avoid this. We want a way to actually bin down our documents into smaller groups that we can then run pairwise comparison on. And in order to do this, we're going to apply a principle called locality sensitive hashing. And so if you remember from here, the more sort of min-hash signatures that we compute from here, the better our estimate becomes. We can actually just relax this requirement and look at that same signature matrix that was permuted and just minimize the number of rows that we're actually comparing. And then we can say that if any discrete group of rows matches exactly, that constitutes a candidate duplicate. And so as you can imagine, this doesn't give us the best estimate of Jacquard similarity, but probabilistically it will pair together documents that are above the threshold of Jacquard similarity that we've actually designated for the run of the algorithm.
So just about 2 more minutes.
Yeah, gotcha. So if we need to actually process billions of documents, this still isn't enough because the actual algorithm grows linearly in the number of documents that we have. And so one example of this is like running this on Polaris, you would need almost 30 nodes to fit this traditional MinHash LSH index into RAM. And so to solve this, we can actually apply a space-efficient probabilistic data structure called the Bloom filter. I'll skip over the actual implementation of this, but the only thing that you need to know is that the only thing that this requires to store it is not a prefix array, it's not a suffix array, or a tree, or a table. It's just a bit array. And so you can actually end up replacing the entire index, which is either usually a prefix tree or a table, with a set of bit arrays, and you can get a massive reduction in space for essentially the same probabilistic guarantees in terms of whether or not your documents match in terms of Jacquard similarity. And so in order to do this, you just take this same LSH principle, and rather than computing it by inserting items into the index, you can actually just map them to a Bloom filter. And this ends up giving you roughly an 80x reduction in index size with virtually no overhead in false positive or false negative error. And so where we get this 80x reduction number is from processing over 100 billion documents. So if you process over 100 billion documents and you alter the hyperparameters of your Bloom filters to get a false positive probability overhead of 1e to the minus 11, which means that in expectation you will only get one false positive out of 100 billion documents, you get this 80x reduction in index size, which is roughly commensurate to the difference in size between a 45-story skyscraper and a 6-foot tall human being. And so, as far as how we're going to extend this next to continue to make this more scalable, we're going to actually parallelize this algorithm. We're going to explore more variants of the Bloom filter, which might offer significant benefits, particularly for particular domain applications. And we're actually going to try to get back something that we lost, which I didn't have time to go over here, but essentially, with our current algorithm, LSHBloom, you can only tell yourself whether or not a document is duplicated. You can't actually get back pairs of duplicate documents. But there's ways that we can actually approach this and still use Bloom filters and enjoy the space savings that we did before. And yeah, I'd like to just acknowledge some of the people who helped.